Ah, welcome. Here we are at the last assignment before our well-deserved and needed spring break. Um, I thought about starting something brand new, but then realized, you know what, that just doesn't make sense right now. So let's just spend a little bit more time on the levers. We're gonna have to not be able to do the lever activity I really wanted to do with the meter sticks and balancing, and figure out how the center of gravity, essentially the weight of the meter stick, would play a role when balancing in real life. And I wanted to teach you how that works, but I really looked for some online resources that explains that, and unfortunately, I just couldn't find anything that was accessible to go over that. But essentially, the weight of the meter stick just becomes another FD during the calculation, so it's really not that hard. But given that we have two essential classes per week now, I'm going to decide to cut that and just kind of focus on the more practical aspects that you will definitely see in other physics classes, including torque and angular acceleration. I hope that you think about levers and simple machines as you look at the world around you. Um, the photo on the right here I found was in Philadelphia 2016, so about 4 years ago, when they were constructing something that looks like it's by 95, I think that is. Not really quite sure it is, but I could be wrong, so don't hold me to that. But essentially, whenever you look downtown, you see the construction, you see these giant cranes. And when you look at these cranes, it's essentially a giant lever. You got the pivot point right there, fulcrum. It's lifting something over here. And you might notice that there is a short distance, and a close-up photo of that would yield there is a massive weight here. This is called a counterweight. All of these cranes need to have a counterweight. Counterweight. Because if they are lifting things at extreme distances, which they have to be extreme distances because the cranes simply cannot be they need to be able to move things over for a practical purpose of construction, lifting and moving things over laterally like this. It's very practical for construction that the crane can hit the entirety of the building, so you don't just have to lay it down and then roll it to where you want it to go. You want it to be able to go exactly where it's going to be in the building. If you put stuff on the crane over here, this is incredible torque. It is a large distance from the fulcrum point. So to prevent the whole thing from just tipping over in this way, what you need is a counteracting torque on the other side. The giant counterweight on the other side provides counteracting torque and actually helps keep the whole crane balanced. It is a simple demonstration of levers and torque that you probably have seen and never thought about, because why would you? But I want you to understand that this concept of a counterweight is all over the place in the world we live in. Elevators actually work with a counterweight. If you don't know how an elevator works, it's fascinating. You should go Google it. But they absolutely work with a counterweight and pulleys. So you know what? It's a pulley, so we might learn a little bit about elevators. We'll see. All I want you to recognize is that these giant cranes are nothing more than the exact lever situations that we have already looked at. You have a huge weight at a short distance can counterweight a huge weight at a short distance here. Big weight, short distance here can counteract a reasonable weight at a longer distance. That's how those cranes work. So torque, as you know, is the torque. Okay, so here's the actual equation, because I'm going to give you a Khan Academy where I want you to actually solve for it. So at this point, I want to give you the symbols. This is the Greek letter tau right here, and tau stands for torque. Torque equals perpendicular force times the distance from the fulcrum. I cannot have you forget d is the distance from the weight to the fulcrum. D is the distance from the weight to the fulcrum. D is the distance from the weight to the fulcrum. So this picture I found really illustrates it. In this first situation, you've got the wrench around the bolt, and to maximize the torque, you just push completely perpendicularly right here. However, if you were to arrange the wrench like this, like here in situation 2 right here, and press down, Not all your force is perpendicular to the plane. What do you mean by that? So here you go. This is the straight line. This is the axis that the wrench is, a straight line right there. A perpendicular force would be like this. This arrow is no longer perpendicular. So some of the force actually gets wasted. So even though you're pushing the lever 120 newtons in both situations, you don't experience the same torque. You have the same force, but you don't have the same torque because some of that torque is going to the other axes. It's not totally perpendicular. You're going to see what I mean in the next slide. And then the third situation right here, if I just pushed parallel, if essentially I took the wrench, I just pressed it inward, I would actually have zero torque because I don't have any perpendicular force. So we're talking about perpendicular to what's called the lever arm. So this red line here is not perpendicular to the lever arm. This is in essence what torque is. So torque equals perpendicular force times distance. But let's just say this was, I don't know, this was the wrench, and you went ahead and just pressed down on the wrench at an angle. If you press at an angle, you actually get less torque than if you pressed all the way down. If you just pressed all the way down, you would maximize the torque. Totally 90 degrees, total 90-degree angles would give you maximum torque. But if you have to push at an angle, this is what you do. We'd go to our good friend sine and cosine. And if this is the theta, we're going to use the opposite over hypotenuse, which is, of course, sine. So F perpendicular equals F, the whole force, sine theta. Because if you think about it, this is the perpendicular part, this is the parallel part. Now, F parallel is going to be cosine. We don't care about parallel forces for torque. We only care about perpendicular forces for torque. So essentially, your torque equation can be this. If you have an angle, this could be your torque equation. Torque equals F sine theta times distance, because we care about the perpendicular, and the perpendicular equals this, so this goes into this. You see, they are all connected. Degree mode, of course. Okay? And the reason why we know that the perpendicular side is sine is because this is the perpendicular. It intersects at a 90-degree angle, and this is the opposite over hypotenuse, and sine is opposite over hypotenuse. SOHCAHTOA. Yay. So I'm going over this because Khan Academy will have you to calculate this. This is all they want you to use right here. Done. The other thing Khan Academy is going to ask you about is something called angular acceleration. So let's just review a couple concepts. Torque is the force that is exerted at a distance from the fulcrum. And you know that forces produce acceleration. And since an object that is fixed in position will rotate in a circle, a torque produces what's called angular acceleration. Now, the simplest, best example is something that I've seen you all do. So I found this picture, surprisingly hard to find this picture online, of when you would take the ruler and put it on your pencil. And then you would start spinning that ruler like a helicopter on your pencil. Now, if you think about it, you are actually doing angular acceleration experiments without even realizing it. You are torquing that ruler. Because if you wanted it to spin, where would you push to get maximum spin? Almost nobody would push right here, that close to the fulcrum. In order to have more acceleration, you need to have more torque. So in order to get maximum spin, you wouldn't push it here, you'd push it towards the end. You would maximize your torque to maximize your acceleration. You naturally knew this without thinking about it in terms of physics. So here we go. This is what Khan Academy is going to ask you about. So this is like a ceiling fan, like you're looking straight up at a ceiling fan. So the middle thing is the pivot point. Let's pretend it's off, and you just decided to get on a ladder, and you just started pushing it. If you pushed it like this, if you pushed this blade this way, and you pushed this blade this way, would the fan move? No, because you are pushing it in opposite torques. The arrow on the right is counterclockwise. The arrow on the left is clockwise. So those torques cancel out. But you knew that already. You knew that if you really wanted to spin it, you would want to turn this one up, and then this one, I'm going to erase that. This one should be down. Now it spins. It spins. Yes. What if, hold on, what if you had something like this? What if you just pressed it right? Oh, eraser, yes, nice. What if you just pressed it right in the middle, and you just pressed right here? Would it spin? Would it go anywhere? Well, provided that you didn't rip it off the ceiling, no, you really can't spin it just by pressing right there. So be mindful. A couple of Khan Academy questions are going to get a little tricksy on you and be like, if you press it right there, what way is it going to spin? It's not going to spin because you have no distance from the fulcrum. You're pushing at the fulcrum. You're not going anywhere. So here is a question. Will fan 1 or fan 2 have a greater acceleration? And this is what I want you to think about. So will fan 1 have, let's say you have a force like this and a force like this. And you get what I'm trying to do here. A force like this and a force like this. Will fan 1 or fan 2? Let's assume all these arrows are the same length. I know I didn't draw them to scale, but let's just assume that all these arrows are the same length. Which fan would have a greater acceleration? Okay, well, which fan would have more torque? Okay, so this fan right here, okay, it's going to have that much torque and that much torque. Let's just say these arrows are the same, so like this plus this. And let's say these arrows are all the same. That one's going to have that much torque, but look how much torque this one provides. Because the second one, all the forces are equal, because the second one has a greater distance from the fan's fulcrum, it's going to produce a greater acceleration, following the exact same rationale you did when spinning that ruler. Khan Academy is going to ask you questions about which object is going to rotate the most. Whenever you see the circle, it's like the fulcrum, which is why I found this fan example. I kind of want to walk through some samples for you. So try those out. They really aren't too bad. So again, if you guys have any thoughts, problems, comments, or concerns, I'd love to give you a hand. I am here. Send me screenshots, ask me questions. Feel free to Google things like levers in the real world, counterweights, elevators. Try to see how these things actually play a role, because now that you have a little bit of time, or maybe you have some time, it's worth to see how all this physics stuff actually connects in the real world. I always wanted this to be practical for you and to connect to some real life things. So take some time and do that. I hope this is going well, and I don't know when I'm going to see you next, but I hope you all enjoy your breaks. And if you need anything, I am here for you guys. Be well.